now we'll have a talk by Surya Ganguli. He's a physicist, theoretical neuroscientist, and professor of applied physics at Stanford. And he leads the Neural Dynamics and Computation Lab. Won a lot of awards. I'll let him talk about the collapse now.
Okay, thanks. Yeah, it sounds like today's the day of collapse. I'm gonna talk about a different type of collapse, and my title's a Boolean logic statement. We'll talk about collapse and explainable AI, or beating neural power laws. I know this is kind of a mixed crowd that's interested in sort of theory and also the brain and so forth. So it'll be kind of a choose your own adventure talk. So basically, what's on the menu? So the first part I'll definitely talk about. It's some of the latest stuff I'm kind of excited about. Is what kind of implicit biases in SGD in actual deep networks, not just in toy settings, can combat overparameterization to aid generalization, right? And we'll uncover a phenomenon of stochastic collapse that's slightly different from what you've been hearing about today, to much simpler subnetworks with many either dead or redundant neurons. We'll show that collapse of such networks is prevalent and can help generalization. And it provides one explanation for why training with large learning rates early in training for a long time, even after the training losses just plateaued, can be beneficial for generalization. And then we don't have time to cover both of these second parts, but I'll give you a chance to vote on which part you want to hear about. I'll take the vote after we cover the first part. But so option one deals with the question, it's sort of at the intersection of AI and neuroscience. If we have a really good predictive model of the circuit, what the heck do we do with it? Are we just, for example, when we do this in neuroscience, are we replacing something we don't understand, i.e. the brain, with something else we don't understand, just a good predictive model of it? So we'll show how, for example, to apply explainable AI-based methods to model reduce a very good model of the retina, and we'll explain how this one model reproduces decades worth of experiments. So that's option one. The other option, more theoretical, is these neural scaling laws where error drops off as a power law with, say, the amount of compute, the amount of data, or model size, have captured sort of the imagination of industry and academia, but they're kind of unsustainable. The exponents are very shallow, right? So can we beat these neural scaling laws? And we'll use statistical mechanics to develop a theory, at least for data selection, to beat neural scaling laws with respect to data. And we'll apply these algorithms to actually do that. So think ahead, you can start to think about which one you'd rather hear about, but I'll take the vote when the time comes, all right? Okay, so the first part, this implicit bias of SGD. So this is some of our recent work to come out of our lab, done with a set of really talented grad students. A classic question that showed up, even today is, why do overparameterized deep neural networks generalize? They have so many parameters, they're so flexible, why don't they overfit the training data? The key idea is perhaps SGD has implicit biases that don't allow these networks to explore all of function space. So they're not as flexible as you might think they are. At least SGD doesn't allow them to be as flexible as you think as they might look like, depending on their parameter count. There's lots of work on this topic in toy settings and so forth. We're going to provide a new additional implicit bias driven by symmetry that applies very generally to many different deep networks that are not toy models, and we'll show evidence for it empirically. So what's the idea? The idea is that in weight space, there are certain invariant sets, which by definition are subsets of parameter space. In our case, they'll be linear subspaces, such that any initialization within the subspace will remain within that subspace for all future iterates of SGD, no matter what mini batches you choose, no matter what learning rates you choose, no matter what hyperparameters you choose, as long as you're doing SGD updates, right? So if such an invariant set were to exist, it would be a powerful constraint. So what are some invariant sets, right, that do indeed exist? So one is a sign invariant set where basically if you have a neuron whose nonlinear activation function goes to the origin, there's a sign symmetry such that if you kill the incoming weights and the outgoing weights of that neuron, then that will never recover from future iterates of SGD. So that's a linear subspace in all of weight space where the incoming and outgoing weights are zero. And once they become zero, it'll remain zero forever. Another invariant set called a permutation invariant set is where you have one neuron, or a pair of neurons, say, that have the same incoming weight vector, the same outgoing weight vector, and the same biases, right? It turns out once you have that condition holding, no future iterative SGD can break that condition. The way you prove that is super simple. You just start within the invariant set, so the invariant condition holds. You compute the gradient with respect to any example, and you show that the gradient lies within the subspace that obeys either constraint. So you can show that the gradient with respect to every single example lies within the subspace. And then once you have that, you know that all future iterates of SGD will remain in that subspace no matter what mini batch you choose, and no matter what learning rate you choose, okay? Because it's a linear subspace, okay? So so basically, this is the dynamics, the dynamical update equation for SGD. Theta is your parameters. L is the loss with respect to one example. This is the gradient. Because every gradient with respect to every example lies within the subspace, the projection of the gradient to the orthogonal complement is 0. Okay? Yeah. For example, in the case of permutation invariant sets, it's a codimension 3 subspace, a parameter space, because you have 3 conditions. Incoming weights equal, outgoing weights equal, biases equal, right? So it's a codimension 3 subspace. And in any given layer, you have, let's say you have n neurons in the layer, you have n choose 2 such codimension 3 subspaces. So it's as if your parameter space is riddled with these invariant subsets. Now the next question you're probably thinking of is, so what? Like if I start in the subset, which is a codimension 3 subset for any one of these pairs, I'll stay within it, that's great. But will I be attracted to it from a random initial condition, right? That's what the rest of this talk is this part of the talk is going to be about. The gradient can never break that condition. So what that means is the projection of the gradient onto the 3-dimensional subspace perpendicular to this codimension 3 subspace is 0. Or a simpler way to say that is the gradient lies within the subspace, right? Or another way to say that is once 2 neurons become equivalent, SGD can't break that equivalence. Okay? Those are all 3 ways to say the same thing. And the math is just you compute the gradient with respect to every individual example, and you show it lies within the subspace. It's just a couple of lines to check that. Okay? Yep. Yeah, this is without momentum, but I think you can generalize it. So then, as long as the initial momentum vector lies within the subspace, then everything follows. Yeah. Yeah. Yeah, so you're never going to initialize on any invariant subspace, but you can get attracted to it, and that's what the rest of this. Yes, we'll talk about the attraction. That's a major question, yeah, that's the subject of this talk. Okay, so how are we going to prove that at least locally you can get attracted to it, and then in simulations we'll show that globally you're actually attracted to it. So what we're going to do is we're going to model SGD using stochastic gradient flow. Okay, so what we're going to do is we're going to model the dynamics of SGD as a stochastic differential equation in continuous time, right? SGD is a discrete time update process, but to the extent that the learning rate eta is not that large, this can be well approximated by this gradient flow, this continuous time stochastic differential equation. And if you haven't encountered these stochastic differential equations, don't worry about it. I'll try to explain all of it intuitively. Okay, there's a drift term, right, which is just gradient descent on your full batch loss landscape, right? So this models the average of a mini batch. So if I average over all the data points, I get the full batch gradient, right? And that's what the drift term is in the stochastic process. That's the first moment of the random update of diffusion. But then I have to model the second moment, okay? So you're going to get some variability in the mini batch to mini batch gradient, right? And that variability is nothing more than the covariance of these gradient terms with respect to all the examples in the entire data set, yeah? You mean in this one, there's a couple of ways to take the scaling limit, and we took it in a way that we put all of the learning rate in the second term. There's a small reparameterization, but you could have done it in another way where there would be an eta here and a square root of eta here and so forth. Okay. Okay, so basically what you have here is you have this is a random vector whose covariance matrix is just the covariance of the gradients across the entire data set, right? So you're going to have a non-trivial correlated noise driving the update. And that's what's showing up here. So this is a standard white noise process. So just think of it as independent noise coming into every parameter. but it's pre-multiplied by this matrix, okay? And this matrix times its transpose is what's called the diffusion matrix, right? And this diffusion matrix is nothing other than the covariance matrix of the gradients, okay? So this is now a continuous time process that matches the first and second moments of this discrete time process. Okay, and the critical issue, so lots of people have modeled stochastic gradient descent with the stochastic differential equation, but the key thing to think about is the non-trivial, non-white structure of the covariance, right? And what we've shown based on the existence of these invariant subspaces, right, is that the gradient of every single example lies within the subspace, which means the covariance of the gradients has no power in the dimensions perpendicular to the subspace, right? All the gradients lie here, so there can be no covariance along this direction if you're on the subspace, right? So what that means is if I take this diffusion operator and apply a projection operator perpendicular to the subspace, a projection operator onto the subspace that's the orthogonal complement of the invariant subspace, on each side, then I'll get 0, okay? So this is just intuitively what this is saying is the diffusion perpendicular to the subspace vanishes on the subspace, okay? That's really important. That's, in physical systems, diffusion is proportional to temperature roughly, right? So what that's saying is that the dynamics is infinitely cold or 0 temperature on the subspace, right? At least in dimensions perpendicular to it. And that will have important implications for the attractivity of stochastic gradient descent to the subspace. Yeah. It's an approximation that holds for small learning rates, that's right. So all the theorems we're going to prove will be about SGF. We'll derive predictions, and we'll test those predictions for SGD, and we'll see that the approximation is good enough in practice. So now let's give you a very simple example of what can happen when you have a position-dependent diffusion, all right? So let's think about a position-dependent diffusion in a double well potential. I'll explain what the GIF is doing later, but you have a double well potential, and just think of this as your loss landscape for a neural network with one parameter, okay? And you're doing gradient descent on the loss landscape, okay? So your drift term is just the negative gradient of the loss, as it usually is, okay? But now let's imagine for whatever reason, it's gonna just go away, one sec, it'll come back. Let's say for whatever reason, the diffusion term is growing, there should be an absolute value here, but the diffusion term is growing as you get further away from the origin. So this double well potential has a maximum at the origin and 2 minima over here, but the diffusion is large here, and it vanishes to exactly 0 here, okay? So roughly in physical terms, this is like a landscape with a mountain here, and the top of the mountain is really cold, but it's really hot here. So then there are certain phase transitions in the dynamics of this position-dependent diffusion problem, okay, and it has to do with this parameter, this parameter zeta. So let's imagine that zeta is small, so the diffusion term is small, so everything's sort of dominated by the drift. Then what happens is the steady state distribution of this process is it looks like this distribution. Let's make zeta larger. Then the steady state probability distribution spreads out. Now the really interesting thing is if zeta is above a certain threshold, this is what happens. Everything concentrates at the origin, right? This is when this position-dependent diffusion is dominating. The entire process gets stuck at the maximum. It doesn't go to the minimum, okay? And that's what you see here. Now, what's the intuition for that? The intuition for that is if zeta is large, this position-dependent diffusion is dominating everything. It's really hot here, so if the particle ends up here, it's going to be buffeted around by the high-temperature diffusion. But it's really cold here. If it gets to here, it's not going to be buffeted around. So even though the top of the mountain is giving you drift away from the maximum, the coldness at the top of the mountain freezes you there. And it pins you there because it's too hot elsewhere. So if you enter a hotter region, you'll get buffeted back to the top. Okay, that's intuition. I'll give you a mathematical formula about that. Yeah. So for stochastic gradient flow, there will not be, because this is the steady state distribution. For stochastic gradient descent, because of the finite update, it'll bounce around near the top, right? Yeah, and you'll see like simulations where that happens, right? In fact, the position of these points, these specific points, corresponds to a stochastic gradient descent, actually, right? Okay. Oh, so the simulations of these dots are finite size, are SGD at some finite eta, right? So we know that SGF is a good approximation to SGD at some small eta, right? Okay. Okay, so we can prove theorems about this, right? Rather than just wave our hands, yeah? Okay, so we can define, we borrow a concept from stochastic control theory. Like we have to define whether or not a fixed point is stable or not, right? So, or whether it's locally attractive, right? But this is a stochastic process, so we need a stochastic notion of attractivity. So there is such a notion from stochastic control theory called stochastic attractivity, right? It has some epsilons and deltas and so forth, but roughly all you need to worry about is this informal statement. The basic condition for stochastic attractivity is if you want all future iterates to remain close to a set with high probability, there always exists an initial condition that achieves that, right? So roughly it's saying if you want to stay close to it, as long as you're this close to begin with, you'll stay that as close as you want for all future iterates, right? So that's a stochastic attractivity condition, and we can prove a theorem for when you satisfy the stochastic attractivity condition in the double wall potential, and this will formalize some of the intuition that I was giving you. Okay, so because it's a local condition, we only have to worry about the shape of the loss landscape in the vicinity of the fixed point, right, this local maximum, okay? So let's zoom in here and Taylor expand. The Taylor expansion is all we need to prove the local condition. So here's our loss landscape locally near theta, and it's a negative curvature maximum. So we just have a negative, we have a negative quadratic here, right? So this quadratic has a second order, its first non-zero coefficient is second order, right? So it has a second derivative here. That's just a number, and that number will play a key role, right? The more negative it is, the more repulsive the drift term is, okay? Similarly, the diffusion, we're assuming that the diffusion vanishes at this point, and then it's going to grow away from the point. So the first non-zero term of the Taylor expansion is going to be quadratic, right? So you know, this is the growth, and it has and this is the second order term in the Taylor expansion. Okay? The condition for stochasticity is that the curvature of the loss function plus the curvature of diffusion should be bigger than zero, and this is a necessary and sufficient condition in one dimension. So if it's bigger than zero, and only if it's bigger than zero, you'll stochastically collapse to the maximum, right? So basically, what is this saying, right? If the second derivative of the loss function is negative, right, then the deterministic drift is pushing you away. But as long as the diffusion is growing faster than the drift pushes you away, the diffusion will dominate and it'll push you to the origin. Okay? So that's a really funny, non-intuitive fact about stochastic processes with position-dependent diffusion, or another way to think about it is spatially dependent temperature. We're so used to thinking about temperature being constant in a room, right? But just imagine if that part of the room were like, I don't know, really, really hot, like 130 degrees, and this part of the room were like, I don't know, 60 degrees. We would all be down here, but for different reasons, because we prefer this location. But if we were particles, if this was zero temperature and that was really high, eventually we'd all get stuck here, right? Okay. We can generalize this to a sufficient condition in higher dimensions, a sufficient local condition in higher dimensions. So roughly this theorem, we don't need to digest it carefully, but what this theorem is saying is a generalization of what we saw in the previous thing in one dimension. Again, the second derivative in any direction normal to the subspace, you know, has a term, you know, as long as this term coming from the loss function and terms related to the strength with which diffusion grows perpendicular to the subspace, as long as the sum of these terms is bigger than zero, then you'll be locally attracted to the subspace. So roughly the intuition is, in higher dimensions where you have a subspace and a higher dimension orthogonal complement, as long as the diffusion tensor in every direction perpendicular to the invariant subspace, as long as it grows sufficiently quickly to counteract the drift terms perpendicular to the subspace, you'll be attracted to the subspace. Okay. Okay. Now, Now you might be asking me, great, like is this stochastic collapse still just a theorist's fantasy? Like you've shown they exist, you've shown that under certain conditions you can be locally attracted to it. Do those conditions hold in practice? And B, even if you can be locally attracted to it, if you start from a completely random initial condition, will you actually get attracted to it, right? In practice, can you see it? So we did some simulations to check that. And surprisingly, like even to our surprise, we saw strong stochastic collapse, say, to permutation invariant subsets. So what we did is we trained a VGG16 on CFAR10, a Resonate 18 on CFAR100. So these two rows are two different experiments. And we checked for stochastic collapse to permutation invariant subsets. So what we did was we took all the incoming weights to each neuron, right? And we hierarchically clustered them according to their cosine similarity, right? This is the outcome of the similarity matrix of hierarchical clustering. And you can see there are lots of blocks of neurons that all have very similar incoming weight vectors, right? Then we took the outgoing weight vectors and they plotted their similarity matrix in the same order that we got from the hierarchical clustering of the incoming weight vectors. And we saw a very similar pattern here, which tells us that pairs of neurons that have similar incoming weight vectors have very similar outgoing weight vectors. And it turns out they have very similar biases as well, right? And there's many, many blocks where you have blocks of similar neurons. So this is collapse to close to an invariant, a permutation invariant subset. Now each row corresponds to a different layer, right? This is conv 11 of the VG16, conv 12, and so forth. Early layers do not collapse, okay? Now why is that? It turns out that there's an expansion in the VGG16 architecture where at some point you go from 256 channels to 512 channels. And it turns out all the layers that do collapse are after this expansion. The ones before don't collapse. Okay? Oh yeah, I have that? Okay. So to come up with a convenient scalar measure of the stochastic collapse, what we did is we computed the fraction of independent neurons in a layer. So what we mean by that is we just set a very small tolerance, say a 1% tolerance, and we asked if there are any pair of neurons whose incoming and outgoing weight vectors are equal to each other within 1%, then we just call them the same neuron. And so all of these neurons would be considered the same neuron then under this measure, and they'd just be considered one independent neuron. And so we computed the number of independent neurons and divided by the total number of neurons. And so that's a measure that measures just the fraction of independent neurons. So if you have a small fraction, then you have a strong stochastic collapse, right? Okay, so we plotted the fraction of independent neurons as a function of layer for the VGG16. And you see exactly that right between conv 7 and conv 8, where the number of channels goes from 256 to 512, is when the stochastic collapse starts happening, okay? For the ResNet, there's interesting oscillations in which layers you get more stochastic collapse, and that has to do with the residual connections, which we have a theory for as well, but I won't go into the details of that, okay? So at least what this is showing is that stochastic collapse is not a theorist's fantasy, it actually happens in practice, okay? All right, so now, okay, so what is it good for, okay? Yeah, do you have a question? Yeah, so what happens is the permutation invariant condition becomes more stringent if you have the residual connections, because you have to take those into account as well. So, but there still are certain layers in which you get it, right? Yeah. So if you want details about when that happens and why, it's in the supplemental material of the paper. Like, it's a bit technical, so I don't want to spend too much time on it. Okay, so the question is, what is stochastic collapse good for? It turns out it can help with generalization, okay? And basically what it means is that these permutation invariant sets are actually saddle points in the weight space of a neural network. They're higher training error saddle points because you can always get to lower training error by having the neurons specialize. But it turns out that these higher training error saddle points have better generalization error, it turns out. And we can show that in a linear student-teacher setting, and then we can also test predictions of that in the for full neural networks. Okay. Yeah. So let me discuss the case of a linear student-teacher the linear student-teacher setting. Okay, so I'm going to review some old work, by Andrew Sachs, Andrew Lampinen, myself, and Jay, on understanding generalization in the linear student-teacher setting for full batch gradient descent. So that work was all for full batch gradient descent. We're going to generalize it to stochastic gradient descent. And then we'll see that there's very different dynamics there between stochastic and full batch gradient descent. And there'll be some generalizable lessons for more general networks that we can extract from that analysis. Okay, so let's review some old work. Okay, so imagine that we just have a 2-weight layer neural network, a linear. It can be generalized to multi-layer linear, but the essential features show up in the 2-weight layer linear. So the learning dynamics is nonlinear because the error function just with squared loss is quartic in the weights, so the gradient is cubic in the weights. If you write down the gradient descent equations, again, full batch gradient descent equations, you get these nonlinear ODEs that, as promised, are cubic in the weights. They're driven by the second order statistics of your data, right? In particular, sigma 1,1, which is the correlation matrix of the inputs, and sigma 3,1, which is the correlation matrix between inputs and outputs. So sigma 3,1 is a matrix that tells you how correlated is one input neuron with one output neuron across the training set. Okay? So it's the expected value, literally, of YX transpose. Okay, we're going to work in a simplified setting where we assume that our inputs are white, so sigma 1,1 is 1. So then everything that drives the dynamics of learning is sigma 3,1, right? The input-output correlation matrix. Okay, for this setting, we can derive exact solutions to the learning dynamics of full batch gradient descent, but for a very special class of initial conditions. But it turns out that class of initial conditions is attracting for the full set of initial conditions. But basically, what we can show is that for this special class of initial conditions where the singular vectors of the student are aligned with the singular vectors of sigma 3,1, the training data, all you have to worry about is the singular values of the students and how they evolve in time. So this is how the singular values evolve. They're this particular function that rises like a sigmoid. And so basically what happens is the learning dynamics learns the singular modes of the training data of sigma 3,1, mode by mode, until eventually the product of weight matrices of the teacher equals sigma 3,1. Okay? So so let's imagine that sigma 3,1, this matrix, has a certain singular value decomposition with singular values given by S, S1, S2, S3, and so forth. Okay? What do the singular modes of the student look like? If you start them from small initial conditions, the singular values of the student will look small, and they'll rise like a sigmoid, and they'll eventually equal the corresponding singular value of the training data, sigma 3,1, right? The time of this rise occurs at 1 over the singular value of the training data. Yeah. So that's just what falls out of the solutions to the learning dynamics. So sigma 3,1, which drives the learning, has a certain singular value decomposition, right? The product of the weight matrices, so W32 times W21, that input-output map has a certain singular value decomposition that's time-dependent because it evolves over training time. What I'm describing for you is how do the singular values of this product matrix evolve over time. The answer is they start small because your initialization is small, and they rise to the corresponding data singular value of sigma 3,1, but they rise in a sigmoidal fashion. Okay? And this is what that rise looks like. So for a particular singular mode of the training data that has a singular value S, it'll eventually rise to S, and this transition will happen at time 1 over S. So a kind of a poetic way to state it is for this setting, stronger statistical structure in the data is learned earlier, right? That's probably also true in nonlinear deep learning. The problem is we don't know how to quantify the strength of statistical structure in data, and we don't know how to predict the learning time as a function of the strength of that statistical structure. But in this linear setting, we know how to answer both of those questions. The statistical structure in question are the singular values of the input-output correlation matrix of the training data, and the time of learning is 1 over the singular value. Okay? Another way to think about it is the learning modes, the modes of the student learn the modes of the training data independently. And so you could think of this as a single mode or just a single network, right? And you could think of the loss landscape as just the singular value of the training data minus A times B, the weight of the first layer and the weight of the second layer. This is your loss landscape, right? If you just think about a single mode, or equivalently a 2-layer network with 1 neuron in each layer, right? 2-weight layer network with 1 neuron in each layer. And this is your loss landscape. It's easy to see what the global minima of these loss landscape are. They satisfy the equation AB equals S. So that's a hyperbola with these 2 branches. These are the minima. It turns out AB equals 0 is a saddle point, actually a maximum. And the learning dynamics in AB space look like this, right? If you start here, you'll evolve to here. If you start with A equals B, you'll have A equals B forever and so forth. So this is the loss landscape for a single mode, yeah? Why do the smaller singular values take more time to learn? What happens is if you start from small initial conditions, you'll be stuck at the saddle point, okay? You'll be close to the saddle point. And the escape time of that saddle point corresponds to 1 over the singular value. So if the singular value is large, the curvature around the saddle point is large, and so the escape rate is fast. If the singular value is small, the curvature around the saddle point is small of the loss landscape, so therefore the escape rate is large, right? That's literally it, right? Of course, you can just you can also just analytically solve the nonlinear ODE and get this formula and see that that's the case, right? Okay. This intuition about this interesting loss landscape for a very simple network will become more important, even more important, when we discuss stochastic collapse in this setting, when we go beyond full batch gradient descent to stochastic gradient descent. Okay. So, are there any questions about this? At least if you forget everything I said, right? If you think about just this like 3 neurons, 2 weights, and this loss landscape, this should be completely clear, right? Okay. Because a lot of the intuition for what I'm talking about can just be obtained from this left column. Okay? In fact, this solution is a solution to the dynamics of this trajectory when A equals B, it turns out. Okay. All right. So another way to think about this is that here we were talking about each mode, when does it get learned? It gets learned at like some time given by 1 over the singular value associated with that mode in the data. But you could also ask, at any instant of time, which modes in the data have I learned and which ones have I not yet learned? So if I fix an instant of time and ask how much is a mode learned, so what I can do is I can think about the singular value of the of the student, which I'll call S, divided by the singular value of the data, which I'm now going to call S hat here, and I look at that fraction. This is a measure of what fraction of the data you've learned already, right? And you can think of this learning process as a singular mode detection wave that sweeps in from large singular values to small singular values. And as this wave sweeps in, you've learned all of the singular mode structure in your training data where the singular values are larger than capital T, the time of learning, and those that are smaller than little t are not yet learned. Right? So that kind of makes sense. If you train for a certain amount of time, you've learned some large modes and you haven't learned the small modes yet, right? So that's what's happening is for the learning dynamics. The singular mode detection wave will become important for trying to understand generalization. Okay, yeah. Okay, we haven't discussed the teacher yet. We've only discussed the dynamics of the student for an arbitrary training data set, and the sufficient statistics of that training data set that drive learning are sigma 3,1. And sigma 3,1 is just this correlation matrix between inputs and outputs, i.e. the expected value of yx transpose. Okay? So we haven't discussed a teacher. The teacher is now going to generate training data that will eventually determine a sigma 3,1. We're going to shift to that now, right? So literally all I've told you is that if I have an arbitrary training set, this is what the dynamics of the student will be. Okay? Yeah. So I've kind of divided the problem up into what is the dynamics of a student learning for any data set, and then I'm going to now create the data set from a teacher, and then I can discuss generalization error. So far, I can't discuss generalization error because I haven't discussed a model for the data. Okay, so now this is a student-teacher setting, okay? We're going to imagine that we have a low-ranked teacher, right, that has some ground truth weight matrices, these bars. So the over bars represent the teacher always. All that really matters is the composite weight matrix of the teacher. It's a low-rank matrix W bar. I'm going to assume that I'm going to generate labels that are the inputs, we have random inputs that pass through the teacher, and then the output is corrupted by noise, by IID noise, okay? So that noise will be important because what it does is it buries the teacher in the training data, okay? Now remember, we know that the dynamics of the student is governed by the input-output correlation matrix of the training data, sigma 3,1. So what is sigma 3,1 in a situation where you have a teacher where you feed in random inputs, you get the outputs, and you corrupt it by noise? It turns out a simple calculation shows you that sigma 3,1 is nothing other than the teacher plus a noise matrix, okay? So this is exactly how the teacher is buried within the training data, right? The statistics of training data that drives learning contains within it the teacher, but it has a perturbation by a noise matrix, okay? So this is an interesting random matrix, and now random matrix theory starts to play a role in the analysis. It plays an important role. Because what we have is we have a low-rank matrix perturbed by random noise, okay? And this is a famous problem in random matrix theory, and the spectrum and the singular value spectrum and structure of sigma 3,1 and its relationship to the teacher is well understood from existing random matrix theory. So now let me review that. So here's the basic idea. You know, remember, sigma 3,1, the correlation matrix of the training data, is what drives learning, but the teacher is what determines generalization. So what is the relationship between the singular value structure of sigma 3,1 and the singular value structure of the teacher, right? Well, the teacher is going to have some singular value decomposition. That's a specification of the problem that has a real singular values, S bar, okay? The training data has some the training data correlation matrix has some singular value decomposition given by the S hats and the U hats. So the training data has the hats on it, the teacher has the bars on it. The question is, what is the relationship between the singular vector of the training data and the singular vector of the teacher, okay? It turns out it depends on the strength of the teacher, i.e. the singular values of the teacher, and in particular their relationship to the variance of the noise, which we're taking to be 1 here. Okay, so what I'm plotting here is the overlap between U hat alpha and U bar alpha, right? The training data dotted with the teacher, as a function of the strength of the teacher, right? What's interesting is if the singular value of the teacher is small, then what happens is the training data can't detect that mode of the teacher. And so the overlap between the training data singular vector and the teacher singular vector will be 0, actually, right? But then there's a sudden phase transition where if the singular value of the teacher is larger than a certain threshold, there will be a non-zero overlap between the singular vector of the training data and the singular vector of the teacher. And then it'll become large and become larger and larger as the singular value of the teacher becomes larger. Yeah? No, the singular value of the teacher is the signal, right? Because remember, yeah, the training data is like W bar plus noise. So the singular value of the teacher is the signal. I want the teacher to have large singular values so I can see it buried within the additive noise, okay? What really matters is the ratio of the singular value of the teacher to the variance of the noise. And I'm working in units where the variance of the noise is 1, so I don't have to worry about that, okay? When I analytically compute the generalization error, I can compute it for any choice of S bars you give me. What I'm showing you is I'm showing you the dependence of U hat alpha with the dot product of U hat alpha with U bar alpha as a function of S bar alpha. So this formula holds for every single singular mode independently, right? Now, if you have multiple singular modes, they'll have different singular values, and so then there'll be an interesting learning dynamics that happens, which we're going to talk about next, right? But by the way, what about the singular values, right? It turns out if you're beyond this phase transition, then the singular value spectrum of your data matrix, sigma 3,1, will have an outlier singular value corresponding to the signal, and the associated singular vector will have some non-trivial overlap. But if you're in this regime, then the training data singular values will be buried within this noise spectrum. So for example, if the teacher were 0, right, then you just have the singular value spectrum of a noise matrix, and that has a well-known Marchenko-Pasteur distribution, and that's this bulk. So this is all you would see if you had a 0 teacher. If you have a teacher with a small singular value, that's again all you'd see. If you have a teacher with one large singular value, suddenly you see an outlier singular value in the noise, in the training data. Yeah? Yeah. So because these are unit vectors, the dot product is between -1 and 1, but you always resolve the sign ambiguity so it's positive. Right? Okay. So this is how the teacher is buried in the data. Now with these formulas, we can analytically write down the training error as a function of time and the test error as a function of time for an arbitrary teacher. Okay? Yeah. Okay, so here's an example of some learning curves. Here's the training error, here's the test error. The solid curves are theory, the triangles are experiments. There's a nice match between theory and experiment. And this is for a situation where you have a rank 1 teacher, okay? And that rank 1 teacher has a large enough singular value that it pops out of the noise and there's a non-trivial overlap between the training data singular vectors and the teacher singular vectors. Okay, so ignore, for example, these singular modes. So how does the training process look like? Can you get a gut, intuitive, like visceral sense of what's happening during training? You can through the singular mode detection wave picture, right? So now you have a singular mode detection wave that's sweeping in from small times to large times. Every time it sweeps over a singular value of the training data, it detects it and it incorporates it into the student, right? Now this first singular mode, when it detects it, that singular mode's singular vector structure is correlated with the teacher. So you learn something both about the teacher and about your training data. So when the singular mode detection wave sweeps over this thing, the training error drops and the test error drops, right? Oops. Okay. Then nothing happens for a while, right? Nothing happens for a while because the singular mode detection wave is still traveling. Then it starts to enter the noise associated with the details of the training data, okay? So now as it penetrates the noise, it continuously starts picking up information about the training data, but it picks up nothing about the teacher, right? Because this is all noise, right? So then what happens is the training error drops continuously, but the test error rises, and that's the nature of the overfitting. You can combat this overfitting in full batch gradient descent only by early stopping. So you can stop early here, and that corresponds to terminating the singular mode detection wave such that you've detected the large singular values, but not detected the small singular values. And that's the right thing to do because the large singular values contain information about the teacher and the small singular values only contain information about the noise. Yeah. In the full learning dynamics, the singular vectors of the teacher start to align with the singular vectors of the training data, right? They never see the teacher, like the teacher's just implicit in there, right? So you align with the singular vectors of the training data, and then the singular value of the student aligns with the singular value of the training data. It's a cooperative effect where they both go up together, right? Okay. So that was a lot to talk about. You can generalize this to 5 layers. It all matches. You can even put ReLUs in the simulations, and the global structure of these learning curves don't change, right? Like, this all survives changing linear to ReLU, like you get the same structure, okay? All right, so now that's old work, by the way. Okay, so now, what happens when you go from full batch gradient descent to stochastic gradient descent, okay? So now we have a saddle point here, right? And just like remember that double well potential I showed you, if the diffusion is strong, you can collapse to the maximum. How do you make the diffusion strong? You make the learning rate large, and you make the mini batch size small, right? That's how the diffusion becomes strong. So then, eta is your learning rate, and beta is your mini batch size, okay? So now if you work out the curvature conditions that I talked about and turn those conditions into the parameters of this problem, right? Now S hat is this should be an S hat here. So S hat is the true singular value of the training data, right? We get a condition that as long as S hat is less than the learning rate over beta, then this maximum here is actually stable, right? So full batch gradient descent, if you start close to here, i.e. with small initial weights, you will go always to the global minimum. But if at high learning rate and small mini batch sizes, you will instead stochastically collapse to 0, right? Okay, now this is actually fantastic. This will help with generalization because of the following, right? Remember, what happens with full batch gradient descent, at any given time t, the large singular values of the training data are learned, and the small singular values are not learned. So if you want to control where you terminate the learning, your only thing you can play with is the optimal early stopping time. But for stochastic gradient descent, it doesn't matter how long you train for. All the modes that are small, where small is set by learning rate over batch size, never get learned. So you can control how large or small the modes are by tuning the learning rate and the mini batch size in a controllable way, right? Okay. Now this can be a good thing for generalization because remember, the small singular values are the noise singular values, right? You don't want to learn the small ones. They're just noise. You want to learn the big ones. They're the signal. So it's actually beneficial to set the learning rate and the mini batch size such that all the singular modes of the training data that are small are set to 0 in the student. It's like a low-rank regularization, right? Okay. Now this has interesting implications, and I think a more generalizable take-home message in terms of the loss landscape geometry, okay? The loss landscape geometry of this two-weight layer problem has been well understood for many years. It turns out that this is kind of the picture. There are many manifolds of critical points, both saddle points and minima, okay? In this two-weight layer setting, you have a manifold of minima, right? These two hyperbolas, and you have one saddle. For the full kind of, n-dimensional problem, you have many, many saddle points, manifolds of many different indices, where index is the number of negative curvature directions, but you only have one manifold of minima. Okay, why is that? It turns out that every assignment of the student's singular values to some number of data singular values, and the rest of the student's singular values are 0, right? So imagine you have a full rank student. Let's say k of the singular values equals k of the data singular values, but the rest are 0, okay? It turns out that's a saddle point. And it's a high training error saddle point because you can always do better by turning on the non-zero singular values of the student, okay? So almost every single extremum point is a saddle point in this problem. It turns out there are no local minima that are not also global minima, okay? What is the global minimum? The assignment in which the top singular values of the student are equal to the top singular values of the data. So i.e. all the data student singular values are turned on. That's the global minimum, okay? So what this is saying is that the best generalizer for this setting of low-rank teacher plus noise is actually a saddle. You don't want to get to the global minimum. You want to get stuck at a saddle, and stochastic gradient descent will exactly help you get stuck there, right? So this leads to a very interesting kind of non-intuitive statement. Higher training error saddle points can achieve lower test error than lower training error minima, and stochastic gradient descent will get attracted to this high training error saddle points, and therefore and you have good generalization there, right? Now, we've looked at Hessians of various neural networks after you train them for a long time, and you always get a small number of negative eigenvalues of your Hessian, even after the training is done. I was puzzled by that. I was like, did the training not work? Like, I never found a local minimum. But actually, this kind of explains why. If you're doing stochastic gradient descent, you're much more likely to be attracted to a saddle. Okay, yeah. Yeah, so I'm going to get to that. Like, can we now exploit this to our benefit, right? The key idea is changing the learning rate changes which set of saddles are attracted or repulsive. And we can engineer that. And that's actually what we have been doing all along as a community. And I'll explain that by training at high learning rates early in training, okay? So, so we quantitatively tested our theory in deep linear networks, and we got a really nice quantitative match between theory and experiment. The solid curves are theory, the dots are experiment, everything matches up. But let me actually move to the results. So this made a prediction, right? So what prediction does it make, right? This says that if I work at high eta, then very negative curvature directions will be attractive. But then if I drop eta, the same negative curvature directions will no longer be attractive, but the shallower ones will be. So I can control which saddles I get attracted to by changing eta, okay? So it turns out a very, very common practice in deep learning, we verified that in the linear networks, and this made a prediction. If you train at high learning rates initially, you'll stochastically collapse to a saddle with many permutation invariant neurons. And then if you drop the learning rate, it'll be hard to escape from that saddle, so you'll be stuck with those permutation invariant neurons. You control the capacity of the network, and you get better generalization. Okay? And that's actually what happens in practice. So here's an example. So now these are real experiments. You don't have to trust me as a theorist anymore. Now you have to trust me as an experimentalist. Or more precisely, you have to trust my students as an experimentalist. And just so I tell you, I trust them. They're really good. Of course, I debug their experiments and stuff, but they all make sense. Okay, so again, we're back to training a VGG16 on CFAR 10, a Resonate 18 on CFAR 100, and so this blue curve is the test accuracy, this gray curve is the loss, the training loss. We're training at a high learning rate, okay? So we're training at a high learning rate for a very long period of time. So the training loss has plateaued. By the way, if nothing I've said makes sense so far, you can reset and hopefully understand the slide, okay? So the training loss has plateaued, okay? Now, oftentimes we train at a large learning rate for a long period of time, even after the training loss has plateaued, and then we drop the learning rate, okay? Here are 3 possible times at which we could drop the learning rate. This orange time, this green time, and this red time, okay? What happens to the learning curves after the learning rate drop, right? This learning curve is all before any learning rate drops, okay? These curves are what happens when we drop around the time of the learning rate drop. So now this is the origin of time. And this is what happens after the learning rate drop for the test accuracy, okay? And what you can see is that if you drop it early, i.e. this orange time, you're stuck at a certain test accuracy before the learning rate drop, but you get higher test accuracy after the learning rate drop. But if you drop it even later, at the green time, you get even higher test accuracy. And if you drop it even later, you get even higher test accuracy, okay? This is part of the reason why people do this early training at large learning rates. Now, what could be a potential mechanism for it? Well, our theory from the linear network suggests that if you train at a high learning rate, the diffusion is strong, you'll have a lot of stochastic collapse. So maybe what's happening is you get more and more stochastic collapse as you train for longer. And that's exactly what we see, okay? So on these same exact runs, we again computed the fraction of independent neurons, right? If the fraction is small, you have a lot of stochastic collapse, where you have many, many neurons that have the same incoming and outgoing weights. And you see that at the early learning rate drop, there's not much stochastic collapse. At the green learning rate drop, there's more. And at the red learning rate drop that's latest, you have even more, right? So you see a correlation, at least, between more stochastic collapse and more improvement in test error. A similar thing happens for the ResNet, but again, the ResNet is more complicated because you get these oscillations in which layer gives you more collapse. But you do see that at longer learning rates, for a longer period of early large learning rate training, you get both better generalization after the learning rate drop and more stochastic collapse. Yeah. I think of this more as a scientific explanation of why the annealing works. But now you can connect 2 very different quantities to a third quantity, which is curvature of the Hessian, right? So I suspect that you can relate the best learning rate and batch size ratio to the curvature of the Hessian around permutation invariant sets. We haven't done that, but that's something you could relate, right? So the curvature of the loss landscape will depend on both the architecture and the data set, right? So if you have some predictions about the curvature of the loss landscape as a function of architecture and data set for some future data set and future architecture, then you can use this. But in practice, you'd have to measure it first, right? But more generally, I just think of it as a mystery, right? Like, You train longer, you generalize better. Training error has plateaued. What the heck's going on, right? And then our theory, like we never would have done this measurement to begin. By the way, we saw the same phenomenon in the linear network, and we never would have made this measurement had we not seen it in the theory. And then you see that there's this dramatic difference in the degree of stochastic collapse, and so that might be a mechanism. Yeah. This degree of stochastic collapse is all measured before we drop the gradient, before we drop the learning rate. So these are properties of the network at, say, this time right before this time right before this, and this time right before this. Yeah. Again, when the learning rate is high, that will help with stochastic collapse. Why you need the warm-up, I'm not sure. We do know a lot about the very early phase of training. It's very chaotic. So we have other work that shows that like where you end up in the loss landscape is very, very sensitive to your mini batch selection for the first couple of epochs, right? So there's something very chaotic going on in the first couple of epochs. My mental picture for that is, oh, by the way, this picture of loss landscapes. This is from a review article I wrote with my colleagues at Google. We have an annual reviews of condensed matter physics called Statistical Mechanics of Deep Learning. I think that's a good way to start to get an overview of sort of physicists' approach to sort of understanding deep learning. And what happens is, high in the loss landscape, you're riddled with saddles, right? So if you're riddled with saddles, what happens is, you can get to a saddle and you have to decide, do I go to the left or the right? So the kind of roughly the Lyapunov exponent or degree of divergence of the training trajectories should be really large, high in the loss landscape where you're dominated by saddles of high index. That's my mental picture for what's going on there, right? But when we're talking about stochastic collapse, the saddle points that help generalization are usually low index saddle points that have a small number of negative curvature directions. So you don't want to collapse to the saddles up here. Actually, I just made up a theory for why that would help, right? If you start with a random initialization, you're likely to start off high here, but you don't want to get stochastically attracted to these high index saddle points. You keep the learning rate low. Then as you go lower and lower in the loss landscape, you would more and more like to get attracted to these saddle points, you increase the learning rate. It turns out there's a strong correlation between the index of a saddle point and its error. That was another paper that I wrote with Yoshua Bengio many years ago, identifying and attacking the saddle point problem in high-dimensional non-convex optimization. Back then, people were wondering, why don't you get stuck in local minima? And our answer was local minima at high error don't exist in high-dimensional spaces typically. Okay. Early in training, the learning rate is high, right? So that promotes the stochastic collapse. You do shift it down, so then the question is, the initial saddle point that you get stuck at, is that the best one? Or is it better to get stuck at a saddle point slightly lower, right? So that might help, that's why the learning rate drop might help. But yeah, anyways. I mean, the only thing you can really take home with you is that the stochastic collapse phenomenon is correlated with the generalization improvement after learning rate drop. That's the only experimental statement I can tell you. And then we understand why for deep linear networks, right? Okay. And we just have a kind of a story for why. So let me just summarize. So here are the take-home messages, right? Because position, so that's the key take-home message. Position-dependent diffusion is sort of an exotic phenomenon in physics. But it turns out to be a ubiquitous phenomenon in deep learning because the covariance of gradients with respect to examples depends on where you are in weight space, right? And in particular, these position-dependent diffusion constants vanish on invariant sets. So these are like very, very cold sets that can trap SGD dynamics, but not gradient descent dynamics, right? And these invariant sets correspond, for example, two classes are sign permutation invariant networks or subnetworks with dead neurons, right? Okay, SGD will be attracted to these invariant sets. We found local conditions for such attractivity. The basic idea is the diffusion must grow faster, perpendicular to these invariant subsets, and the drift away from them grows. These invariant sets correspond to saddle points, not minima. In two weight layer networks, there are many saddles and only one minimum. All of them generalize differently. And typically the saddles, the higher training error saddles, will generalize better than the lower training error minima. Okay? And Yeah, you can tune the learning rate and batch size to select which saddles you find attractive. And in the wild, like in real networks, ResNets, VGGs, whatever, stochastic collapse is prevalent, and prolonged early learning with high learning rates enhances both stochastic collapse and subsequent generalization. Okay, so I was even too ambitious. I had promised you a vote on, but I think we're done, right? Like, I'm actually just curious to get a pulse on the audience, right? If we were to go forward with the second part of the talk, there's two options. One is neuro AI, using explainable AI to really understand conceptually how complex models of a retina work and extract decimal predictions. Or just how do we beat power law neural scaling using StatMech to bend the power laws down, sometimes even make them exponentials. I'm just curious, if we were to continue, how many would go for option 1? Interesting, okay. And then how many would go for option 2? It's roughly split, but slightly more on the neuro side. So people still care about neuro. Okay, that's good. Good, okay, all right. But anyway, it's a moot point. But I'm actually glad we spent a lot of time in the first part, because hopefully I went slowly enough that something that I could convey some of the ideas. All right, thanks, I'll stop here. Yeah.